Welcome to Why Do Species Go Extinct? A journey into one of the greatest untold stories of our time. Before we begin, take a moment to dim the lights, put on your headphones, and get comfortable. You're about to hear a story that spans millions of years, but could shape the next few decades. If you're enjoying this kind of deep, thought-provoking content, don't forget to like, follow, and subscribe. It helps keep the wild alive in more ways than one. Now imagine a world where forests fall silent, oceans grow empty, and creatures that once walked beside us are only remembered in books and bones. What if it's already happening? Let's begin. Extinction. The word itself carries a kind of finality, an ending. In everyday language, it suggests something is gone forever. But in biology, and in the grand story of life on Earth, extinction is both an end and, oddly, a beginning. It is a natural part of the evolutionary process, a punctuation mark in the history of life that both closes and opens chapters. In this first chapter, we're going to explore what extinction really means. We'll talk about how scientists define it, how it happens, and why it is a fundamental force shaping the diversity of life on our planet. We'll also explore the difference between normal background extinction and the more dramatic events we call mass extinctions. Along the way, we'll examine how extinction is measured, what causes it, and why it matters. But most importantly, we'll lay the groundwork for understanding the complex web of factors, both natural and human-driven, that lead species to disappear. By the end of this chapter, you'll not only know what extinction is, but why it's essential to the story of life, and why the extinction crisis we face today is unlike any in the past. Let's start with a definition. In biology, extinction is the complete disappearance of a species from the Earth. When the last individual of a species dies, whether it's a plant, animal, fungus, or microbe, that species is considered extinct. There's no way back, no hidden populations, no revival. That lineage, sometimes millions of years old, is gone forever. This may seem like a simple definition, but in practice, determining extinction is complicated. For many species, especially those in remote or poorly studied areas, we may not know if the last individual has truly died. Some species are declared extinct, only to be rediscovered decades later. These are called Lazarus species, named after the biblical story of Lazarus, who rose from the dead. For this reason, scientists often use the term functionally extinct as well. This refers to a species that may still have a few surviving individuals, but not enough to sustain a viable population. In other words, they are biologically doomed, even if technically still alive. These may be animals in captivity, or fragmented populations too small to reproduce naturally. One of the most important things to understand is that extinction is not inherently unnatural. In fact, it's always been part of the evolutionary process. Just as new species arise through evolution, old species disappear. In fact, over 99% of all species that have ever lived on Earth are now extinct. This is a staggering number. It means that the biodiversity we see around us today, from oak trees and elephants to jellyfish and jaguars, represents just a tiny fraction of all the life forms that have existed in Earth's 4.5 billion year history. Most of these extinctions occur slowly and gradually through a process known as background extinction. This is the normal rate of extinction that happens as ecosystems shift, climates change, and species compete for resources. A species might lose its niche, fall behind in the evolutionary arms race, or be gradually outcompeted by a more efficient rival. In the fossil record, background extinction has an estimated baseline rate of about 1 to 5 species per year, depending on the group. This background rate serves as a benchmark for evaluating modern extinction rates, and as we'll explore in later chapters, today's rates far exceed it. But sometimes, extinction doesn't happen gradually. It happens all at once, across entire ecosystems. These are known as mass extinction events, and they represent catastrophic intervals in Earth's history when vast numbers of species, sometimes over 75%, disappear in a relatively short geological time frame. Mass extinctions are rare, but they've happened at least 5 times in Earth's past. Each one reshaped life on the planet, wiping the evolutionary slate clean and allowing new forms of life to emerge. You might wonder, how do scientists actually determine when a species is extinct? It turns out, this can be surprisingly difficult. For animals that are well monitored, like large mammals or birds in industrialized countries, extinction can be documented with some certainty. When the last known individual dies, and no others are found despite extensive searches, we can say the species is extinct. But for most species, especially insects, amphibians, and deep-sea organisms, things are murkier. Some may go extinct without ever having been formally discovered or named. Others may persist in remote habitats, unseen by humans for decades. The International Union for Conservation of Nature, or IUCN, maintains the Red List of Threatened Species, which is the most comprehensive global inventory of the conservation status of species. To declare a species extinct, the IUCN requires exhaustive surveys in known or expected habitats across its historic range at appropriate times, and still finding nothing. This is why rediscoveries do happen. The coelacanth, a prehistoric fish thought to have gone extinct 66 million years ago, was found alive in 1938. The Lord Howe Island stick insect, declared extinct in the 1920s, was rediscovered on a rocky island in 2001. These surprises are rare, but they serve as reminders of how little we still know about the full extent of life on Earth. Not all extinctions are the same. Scientists use several different terms to describe the ways and contexts in which extinction occurs. Local extinction. This refers to the disappearance of a species from a particular geographic area, even if it exists elsewhere. For example, grey wolves are locally extinct in much of Western Europe, though they persist in Eastern Europe and parts of North America. Ecological extinction. This happens when a species is still present, but in such small numbers that it no longer plays a significant role in the ecosystem. An animal might still exist, but not in enough numbers to serve its ecological function, such as pollination, seed dispersal, or predation. Functional extinction. As mentioned earlier, this means a species cannot sustain a population. It may be reproductively non-viable, or exist only in captivity. It's a step away from total extinction, but the ecological consequences are already in motion. Understanding these nuances helps us appreciate that extinction is not always a sharp cutoff. It can be a slow fade, ecologically, reproductively, and geographically, before the final disappearance. Later chapters will dive deeply into the many causes of extinction, but here's a quick preview. Environmental changes, such as global warming, sea level changes, or shifts in ocean chemistry, can destroy habitats or make them uninhabitable. Competition and predation may push species out of their niches or overwhelm their ability to survive. Diseases, especially those introduced by invasive species, can devastate populations with no natural immunity. Human activities, including hunting, deforestation, pollution, and climate change, have become the dominant drivers of extinction in the modern age. All of these factors can interact, creating what scientists call extinction vortices, in which one problem compounds another until the species can no longer recover. Now you might ask, if extinction is natural, why should we be concerned? Here's why. While background extinction is a slow and relatively balanced process, what we're seeing today is not normal. Modern extinction rates are estimated to be 100 to 1,000 times higher than background levels, and the vast majority of this is due to human influence. Unlike in past extinction events, this time we are the asteroid. We are the volcanoes. We are the change. An extinction doesn't just remove species, it unravels ecosystems. When key species disappear, pollinators, predators, keystone species, entire ecological networks can collapse. That affects everything from food security and clean water to medicine and climate regulation. Biodiversity is not just a nice to have, it's the infrastructure of life on Earth. Extinction, for all its finality, leaves behind a story. It's written not in ink but in stone, preserved in the layers of rock and sediment that make up the Earth's surface. These layers, stacked over millions of years, hold the remnants of creatures that once lived, breathed, swam, crawled, and flew. This is the fossil record, our greatest archive of the history of life on Earth, and the most powerful evidence we have that extinction is not only real, but deeply woven into the fabric of evolution. Before humans had a concept of extinction, many cultures believed that every species that ever existed was still alive somewhere, hidden perhaps in distant corners of the world. It wasn't until the late 18th and early 19th centuries that scientists began to seriously consider the possibility that species could completely vanish from the Earth. One of the earliest clues came from fossils of animals that resembled modern species, but were clearly different: mammoths, giant sloths, and strange reptiles with unfamiliar shapes. If these creatures were still alive, surely someone would have seen them. But no one had. French naturalist Georges Cuvier was among the first to propose that these fossilized creatures were not just odd variants of modern animals, but belonged to species that had died out. Through detailed comparisons of skeletal anatomy, Cuvier demonstrated that these creatures had no living counterparts. From this foundation, paleontology, the scientific study of life through fossils, began to take shape. With it came the dawning realization that extinction was not only real, but common. As paleontologists dug deeper into the Earth's layers, they uncovered more than just ancient bones. They uncovered patterns. Species appeared, thrived, and then disappeared, sometimes slowly, and sometimes all at once. The farther back in time they looked, the more dramatic these disappearances seemed. They noticed intervals in the rock record where vast numbers of species vanished, seemingly in the blink of a geological eye. These were not isolated extinctions, but global events. They came to be known as mass extinctions. There have been 5 major mass extinction events in Earth's history. Each one marked a turning point in the evolution of life. Each one reshaped the biosphere in profound ways. The first, the Ordovician Silurian extinction, occurred around 443 million years ago. At the time, life was mostly confined to the oceans. A sudden drop in global temperatures triggered a glaciation event, drastically lowering sea levels and wiping out an estimated 85% of marine species. The planet rebounded, but life was forever changed. The second event, the late Devonian extinction, unfolded around 375 million years ago. It wasn't a single catastrophe, but a drawn-out crisis lasting millions of years. Reef-building organisms were hit hard, along with many types of fish. The causes are still debated. Possibilities include volcanic activity, climate shifts, and changes in ocean chemistry, but the result was a prolonged period of ecological instability. Then came the most severe extinction event in Earth's history, the Permian-Triassic extinction, about 252 million years ago. Sometimes called the Great Dying, this event eradicated more than 90% of marine species and 70% of land species. It was the closest life has ever come to total annihilation. Entire ecosystems vanished. The causes likely included massive volcanic eruptions in what is now Siberia, leading to runaway global warming, acid rain, and ocean anoxia, a deadly loss of oxygen in the seas. The fourth event, the Triassic-Jurassic extinction, happened around 201 million years ago. It paved the way for the rise of the dinosaurs. Again, volcanic activity appears to have played a role, disrupting ecosystems and allowing certain groups, like the early dinosaurs, to dominate the vacant niches. And then, of course, there is the most famous of all, the Cretaceous-Paleogene extinction, 66 million years ago. This was the event that wiped out the dinosaurs, or at least all the non-avian ones. The impact of a massive asteroid near the Yucatan Peninsula created a chain reaction of firestorms, global cooling, and darkness. This single event wiped out about 75% of species, including ammonites, pterosaurs, and the dominant land reptiles. but it also gave rise to mammals, and eventually, to us. What these 5 events have in common is that they were global, rapid, and caused by extreme environmental change. They didn't just take out a few vulnerable species, they reshuffled the entire biological deck. After each extinction, life rebounded, but in a new direction, new lineages flourished. New ecosystems formed. In this way, extinction has not only ended life, it has also made way for new life. It has been paradoxically both a destructive and a creative force. Still, it's important to understand that these mass extinctions were rare. They span hundreds of millions of years, and between them, life mostly followed a slow, steady rhythm of background extinction and speciation. This long-term perspective is key when we consider what is happening today. Modern extinction rates are not just part of the background noise. They echo the abruptness and severity of past mass extinctions, and they are driven largely by one species, ours. Fossils tell us what was lost, but they also help us understand how life recovered. After the Permian extinction, for example, the recovery of biodiversity took millions of years. It wasn't just the loss of species, it was the loss of ecological complexity. Food webs collapsed, keystone species vanished. Once rich environments became biological deserts. In time, evolution filled the voids, but not quickly. In a human timescale, mass extinctions are permanent, and here lies a sobering truth. If we trigger a 6th mass extinction, a possibility scientists warn is already underway, the consequences will be measured not in decades, but in millions of years. What we lose in a single century may not return for an age, and much of it may never return at all. The fossil record is our warning. It shows us how fragile life can be in the face of rapid environmental change. It shows us that biodiversity is hard-won and easily lost, but it also offers perspective. Life is resilient. It adapts. It evolves. But evolution does not guarantee survival. Extinction is always waiting at the edge of change. So when we look at a fossil, a trilobite, a fern imprint, a dinosaur tooth, we're not just looking at something that died. We're looking at something that once lived, thrived, and contributed to the intricate web of life. We're reading a page from the book of Earth's history, a chapter that closed but whose echoes still shape the living world. In the next chapters, we'll move forward from deep time to modern times and look at the natural causes of extinction, how species disappear even without human influence, and what makes certain species more vulnerable than others. But always, we'll carry with us the lessons of the past, carved in stone, written in bones. Life is dynamic. It shifts, adapts, evolves, but it also fails, collapses, and vanishes. Long before humans walked the earth, extinction was already shaping the evolutionary tree, pruning branches that no longer bore fruit. To understand the current biodiversity crisis, we must first explore how extinction happens without us. Because while humanity has accelerated the pace of disappearance, nature itself has always held the power to end a species. Contrary to the common belief that extinction is unnatural or abnormal, the truth is more nuanced. Extinction is, in a sense, a built-in feature of life on Earth. It is not a malfunction of the evolutionary system. It is part of that system. Just as birth and adaptation give rise to new species, ecological pressures, environmental upheavals, and biological limitations can lead to their end. Let us now turn our attention to the natural mechanisms behind extinction, forces that were in motion long before we arrived, and will continue long after we're gone. One of the most fundamental drivers of extinction is environmental change. Earth is not a static world. Its climate, landscapes, and oceans have transformed dramatically over geological time. Ice ages come and go, sea levels rise and fall, and continents drift across the globe like slow-motion icebergs. These changes, though often gradual, can dramatically reshape ecosystems. Take climate fluctuations. Even small long-term shifts in temperature can make or break entire species. A warming trend might expand tropical zones but shrink cold habitats. Glaciations can trap populations in shrinking refuges. The creatures best adapted to these new conditions may thrive. Those that can't keep up, those too specialized, too slow to adapt, are left behind. In many cases, it's not a single temperature spike that drives extinction, but the cascading effects it unleashes, shifts in plant communities, migrations of predators and competitors, changes in food availability. Volcanic activity is another powerful natural force with extinction potential. Supervolcanoes, like those believed to have triggered the Permian-Triassic extinction, release immense amounts of ash and gas into the atmosphere. This can darken the skies, block sunlight, and cause volcanic winters, periods of global cooling that disrupt photosynthesis and food chains. At the same time, volcanic emissions of carbon dioxide can eventually reverse the cooling and cause long-term global warming. These rapid oscillating shifts are deeply destabilizing to ecosystems. Even today, smaller volcanic eruptions can cause measurable drops in global temperature. In the deep past, they were agents of mass death. Then there are asteroid impacts, the rock stars of extinction stories, quite literally. The asteroid that struck Earth 66 million years ago was no larger than a city, but it brought the age of dinosaurs to an abrupt and fiery end. The impact released the energy equivalent of billions of nuclear bombs, igniting global wildfires, sending dust into the atmosphere, and halting photosynthesis for months. Species that depended on stable climates or complex food chains quickly vanished. The impact was brief, but its consequences rippled across centuries. But these dramatic events are only part of the story. Many extinctions unfold without explosions or lava flows. Instead, they arise from biological and ecological interactions, the complex dance of predator and prey, competitor and collaborator, that defines ecosystems. Consider evolutionary disadvantage. In any environment, some species are better suited to survive than others. Those with traits that improve their chances of finding food, escaping predators, or reproducing successfully are more likely to pass on their genes. But evolution is not a guarantee of survival. In fact, it's full of dead ends. Many species evolve extreme specializations that serve them well until the environment shifts. A giant herbivore that feeds only on a certain tree may thrive for millennia, but if that tree goes extinct, so too might the herbivore. Evolution rewards immediate success, not long-term flexibility. When the rules of the ecosystem change, the most specialized species often pay the price. This leads us to the concept of ecological niches. Every species fills a particular role in its ecosystem, a niche shaped by its diet, behavior, reproductive strategy, and interactions with other species. But niches are fragile. If a competitor evolves a more efficient way to exploit the same resources, the original species may be pushed out. If a new predator arrives, the balance can quickly tip toward extinction. Competition, especially from invasive species, can be brutal. Even in pre-human times, when continents occasionally connected after long separations, waves of extinctions followed. When North and South America joined via the Isthmus of Panama about 3 million years ago, northern animals like bears, cats and horses spread southward and outcompeted many native South American species. Extinction in this sense was the outcome of a biological clash between two long-isolated evolutionary theaters. Predation, too, plays a role. When a new predator evolves, especially one with an efficient hunting strategy, prey species may not have time to adapt. This is especially true when prey have lived in environments without natural predators for long periods. They may lack basic defensive behaviors or anatomical traits needed for survival. Natural selection may eventually catch up, but sometimes the clock runs out first. Another, less obvious cause of extinction is co-extinction. This occurs when the survival of one species is tightly linked to another, such as a parasite with its host, or a pollinator with a specific plant. If the host goes extinct, the dependent species often follows. These are silent extinctions, often invisible to us, but they speak to the intricate interdependencies in nature. Likewise, population dynamics can play a quiet but deadly role. Small populations are inherently vulnerable. They suffer from reduced genetic diversity, making them less adaptable to change. They are more susceptible to random events, a disease outbreak, a bad breeding season, a harsh winter. Even a minor disruption can send a small population into a downward spiral, a process known as the extinction vortex. The smaller the population, the greater the impact of each death, until recovery is no longer possible. Geography matters too. Species confined to isolated environments, islands, mountaintops, deep caves, often evolve in unique ways, but they also live on the edge of extinction. They have nowhere to go when conditions change. Many island species are what scientists call evolutionary relics, remnants of larger groups that once had wider ranges. These species may survive for thousands of years in stable conditions, but are highly susceptible to disruption. Natural disasters, wildfires, floods, tsunamis, hurricanes, also contribute to extinction, particularly when species already have limited ranges. One bad year, one unlucky strike, can erase a lineage forever. These events may be random, but their consequences are shaped by the biological realities of each species: how fast it reproduces, how far it can disperse, how much genetic diversity it holds. Even the passage of time can be a force of extinction. Evolution is not a perfect system, it is a trial and error process. Most species that ever lived eventually disappear, not because of a dramatic event, but because they are gradually replaced by newer, better adapted descendants. This competitive replacement is like nature's slow turnover. It's not violent or abrupt, but it's relentless. Still, nature is not only a destroyer, it is also a creator. Extinction clears the ecological stage, making room for innovation. When dominant species disappear, new forms can emerge and diversify. This has happened time and again in Earth's history. After the dinosaurs fell, mammals radiated into new forms, from whales and bats to humans. After ancient reef systems collapsed, new reef builders arose. The empty niches don't stay empty for long, at least not on a geological timescale. So while natural extinction may seem tragic, it is also a driver of diversity. It is the mechanism by which life renews itself. But what makes today's situation so alarming, and fundamentally different, is the rate of extinction. Natural extinction plays out over thousands, even millions of years. Human-driven extinction, as we'll see in the next chapter, can happen in decades, sometimes in a matter of years. What nature does slowly, we now do swiftly. And what nature does blindly, we often do knowingly. Understanding how extinction happens without us gives us a vital perspective. It shows us that species can, and do, vanish for reasons beyond human control. It reminds us that vulnerability is not new, and that resilience is hard-earned. But it also helps us recognize how much faster and more severe extinction becomes when natural forces are accelerated by human hands. Before we look at how humanity has altered the rules, let's reflect for a moment on what nature has taught us. Extinction is not an error. It is an outcome, the result of life constantly testing, adapting, and sometimes failing. Every extinct species is a reminder of both life's fragility and its creativity. They are not just losses, they are chapters, endings that made new beginnings possible. In the next chapter, we will cross a line in history, from the slow clock of natural extinction to the fevered pace of the Anthropocene. We'll explore how human beings, a single species, have become the most powerful driver of extinction on the planet. And we'll ask a difficult but necessary question: what does it mean to be responsible for the vanishing of life? The vanishing of life. There is a term scientists use more and more these days: the Anthropocene. It's not just a poetic description, it's a proposed geological epoch. a new chapter in Earth's history defined by the global impact of one species, us, humans. For billions of years the Earth evolved without us. Life rose, diversified and vanished, shaped by volcanic eruptions, shifting continents, climate swings, and the occasional cosmic collision. Then, some 300,000 years ago, a blink in geological time, Homo sapiens arrived, and the story changed. The rise of humans marked a fundamental shift. We weren't the strongest or the fastest. We didn't have fangs or claws, but we had something more powerful, brains capable of language, tools, culture, and foresight. That intelligence, paired with social cooperation, allowed us to adapt rapidly, to survive in virtually every climate, and ultimately to dominate ecosystems. We became not just another species, but a planetary force, and with that power came consequences. Our earliest impact on extinction may have been unintentional, but it was profound. As humans spread across continents, they encountered animals that had never experienced an intelligent predator before. Giant sloths in South America, woolly mammoths in the Arctic tundra, flightless birds in New Zealand, marsupial lions in Australia. These megafauna, large-bodied animals, had evolved in isolation, without the evolutionary pressure to fear beings like us. Within just a few thousand years of human arrival in these regions, many of them were gone. This pattern is striking. In North America, nearly 75% of large mammals went extinct shortly after humans arrived. Australia lost over 85% of its megafauna within a few thousand years of human colonization. On islands like Madagascar and New Zealand, unique species vanished at an even higher rate. While climate change may have played a contributing role in some cases, the timing is hard to ignore. These extinctions follow us, a trail of vanished giants wherever Homo sapiens set foot. But it wasn't just direct hunting that drove these early extinctions. It was also fire, habitat disruption, and the introduction of new species, dogs, rats, pigs, that changed ecosystems forever. Even in our most primitive state, humans had the power to transform landscapes and disrupt ecological balance. And as our technologies advanced, so did our influence. The invention of agriculture around 10,000 years ago was a turning point. Humans began to clear forests, divert rivers, and domesticate plants and animals. This was the beginning of the Anthropocene in action, the conversion of wild landscapes into managed systems. Biodiversity declined as monocultures spread, wetlands were drained, natural fire cycles were interrupted. Species that once thrived in diverse, patchy environments struggled to survive in fields and pastures. At first, this transformation was local, but over time, as human populations grew and civilizations expanded, it became global. Trade routes carried species to places they had never been before, not just goods and people, but pests, diseases, and invasive organisms. The Columbian Exchange, which followed European contact with the Americas, introduced pigs to the Caribbean, rats to Pacific islands, and new diseases to indigenous peoples and native wildlife alike. Entire ecosystems were upended in a matter of decades. Then came the Industrial Revolution, the Great Acceleration. Suddenly, human influence was no longer just a surface-level disruption. It was a planetary-scale reconfiguration. Fossil fuels gave us unprecedented power. We built machines that could clear forests, dredge rivers, and mine mountains. We created synthetic chemicals, altered the chemistry of the atmosphere, and pulled more from the ocean than it could replenish. Trains and ships carried species around the globe, mixing once separate ecosystems into a chaotic new world of biological conflict. And with these changes, extinction surged. Today, scientists estimate that species are disappearing at rates 100 to 1,000 times higher than the background extinction rate, the natural pace at which species typically go extinct. This is not speculation. It is based on decades of data, field surveys, fossil comparisons, and statistical models. We are not just losing a few obscure creatures. We are witnessing a mass extinction event unfold in real time. The drivers of human-caused extinction are many, but but they can be traced to a handful of powerful forces: habitat loss, overexploitation, invasive species, pollution, climate change, and direct killing. Habitat loss is the most widespread and immediate threat. Every time a forest is cleared for agriculture, every wetland drained for development, every coral reef bleached by warming seas, countless species lose the homes they depend on. Fragmentation is especially damaging. Even when parts of a habitat remain, they are often cut off by roads, cities, or farms, creating isolated islands of biodiversity that are too small to sustain healthy populations. Species that once ranged widely become confined to shrinking pockets of green, their numbers dwindling as genetic diversity erodes. Overexploitation, through hunting, fishing, and harvesting, has pushed many species to the brink. We fish the oceans at unsustainable rates. We poach elephants and rhinos for ivory and horn. We capture exotic birds, reptiles, and mammals for the illegal pet trade. Some species are wiped out before we even know they exist. Others are driven into captivity, or survive only in zoos. And often, it is not need but greed that drives this pressure. A global economy that treats nature as a resource to be mined rather than a web of life to be respected. Invasive species are another major threat. When humans move plants or animals to new places, intentionally or accidentally, the results can be disastrous. Non-native predators, competitors, and diseases often decimate local species that have no defenses. Brown tree snakes in Guam, cane toads in Australia, zebra mussels in North America, each has caused cascading ecological damage. Sometimes the invaders are microscopic. A single fungal pathogen can wipe out entire species of amphibians or bats, as has happened in many regions. Pollution, once considered a local nuisance, has become a global force. Plastics now litter the most remote corners of the earth, from the deepest ocean trenches to Arctic snow. Pesticides and fertilizers poison soil and waterways, disrupting food chains and reproductive systems. Heavy metals and industrial chemicals accumulate in the bodies of animals, impairing growth and survival. Even noise and light pollution, byproducts of modern life, can interfere with migration, mating, and predator-prey interactions. Climate change, driven by our burning of fossil fuels, is the great amplifier. It doesn't replace other threats, it magnifies them. As temperatures rise, species are forced to shift their ranges, migrate earlier, breed differently. Some can't move fast enough, others find no suitable habitat to migrate into. Ocean acidification, caused by increased carbon dioxide levels, threatens shell-forming marine organisms. Coral bleaching is decimating reef systems. Droughts, wildfires, floods and storms are becoming more frequent and severe, creating stressors that many species cannot survive. And finally, there is direct killing. Sometimes it is deliberate, the eradication of predators to protect livestock, the extermination of animals deemed pests. Sometimes it is incidental, roadkill, bycatch in fishing nets, wind turbine collisions. In all cases, the cumulative toll is immense. What makes all of this even more tragic is that we know better. We understand ecosystems. We can measure population declines. We have the technology to monitor change, to mitigate damage, to protect species. Yet too often, short-term interests outweigh long-term wisdom. Forests are felled for palm oil. Wetlands are paved for shopping malls. Species go extinct because no one was willing to act. Still, there is hope. The very intelligence that made us so powerful also gives us the ability to understand, to change, and to restore. Conservation biology, ecology, environmental science. These fields are filled with people working to protect species, rebuild habitats, and reverse damage. Laws like the Endangered Species Act, treaties like CITES, and protected areas like national parks have saved species from the brink. But time is running out. The longer we wait, the more fragile populations collapse, the more ecosystems unravel, the more potential we lose, not just for biodiversity, but for medicine, agriculture, resilience, and beauty. Every species that goes extinct is not just a loss for nature, but a loss for us, a part of the story that can no longer be read, a voice silenced forever. We are the first species with the awareness to recognize our impact on extinction. That gives us a choice. We can continue down the path of destruction, accelerating the sixth mass extinction, or we can change direction, embrace stewardship, restraint, and responsibility. The Anthropocene is not a destiny, it is a decision. In the next chapter, we will examine what makes species vulnerable to extinction. Why do some species survive even in harsh conditions, while others perish quickly? What traits and patterns put species at greater risk? And how can this knowledge guide our efforts to protect life on Earth? Not all species face extinction equally. Some vanish with the first breeze of environmental change, while others seem to endure almost anything: drought, pollution, even the presence of humans. The natural world is full of survivors and casualties, and what separates them isn't always obvious at first glance. But as scientists have studied extinction more closely, patterns have emerged. Certain characteristics, biological, ecological, behavioral, make some species far more vulnerable to vanishing than others. To understand why this is so, we need to look at how a species lives, what it eats, where it lives, how it reproduces, how far it moves, and how it interacts with its environment. These details determine not just how a species fits into an ecosystem, but how it copes with change, and change is, ultimately, what drives extinction. One of the most important factors in vulnerability is specialization. Some species have evolved to fit into a very narrow ecological niche. They eat only one kind of food. They live only in a certain type of habitat. They rely on a single pollinator, or breed only under specific conditions. These specialists thrive when their environment is stable. They are fine-tuned to it. But that fine-tuning is a weakness when things begin to shift. If the one tree they feed on is logged, or the insect they depend on disappears, they have nowhere else to turn. The world changes, and they cannot follow. Contrast that with generalists, species that can live in many different environments and eat a wide range of foods. Rats, pigeons, raccoons, and crows are classic examples. These species adapt quickly, even in urban environments. Their flexibility makes them far more resilient. When ecosystems are disrupted, generalists are often the survivors, sometimes to the detriment of more delicate species. Geographic range also plays a major role. Species with wide distributions, those that live across continents or in diverse climates, are less likely to go extinct than those confined to small areas. The species restricted to a single island, a single valley, or a particular mountaintop is inherently at risk. One storm, one fire, one human settlement can wipe them out entirely. Endemic species, those found nowhere else in the world, are particularly vulnerable. Their extinction means global loss. Population size is another critical factor. Small populations face a number of challenges. They have less genetic diversity, which makes them more susceptible to disease and less able to adapt to environmental changes. Random events, a bad breeding season, a harsh winter, a single disease outbreak, can have devastating effects. Even slight human interference can tip the balance. Small populations also suffer from inbreeding, which can reduce fertility and resilience. Reproductive rate matters too. Species that reproduce slowly are more at risk. Elephants, rhinos, whales, these animals take years to reach maturity, and they have relatively few offspring. If their populations are reduced by poaching, habitat loss, or environmental stress, recovery is slow, sometimes too slow to overcome ongoing threats. By contrast, species that reproduce quickly, like rodents or insects, can rebound more easily after population crashes. Mobility, or lack thereof, can also determine fate. Species that cannot move easily to new habitats are trapped when their current environments are destroyed. Amphibians, for example, often have very limited ranges and need specific moisture conditions to survive. When their ponds are drained or forests cut down, they cannot simply migrate to new areas. Similarly, coral reefs are built by sessile organisms. They don't move at all. When conditions deteriorate, they die in place. Trophic level, where a species sits in the food chain, also influences vulnerability. Top predators tend to be more at risk than species lower on the chain. Why? Because they need large territories, depend on healthy populations of prey, and often have low reproductive rates. When prey disappears, predators follow. This makes carnivores particularly sensitive to ecosystem disruption. A collapsing food web usually collapses from the top down. Behavior can matter too. Some species have highly specific breeding rituals, nesting requirements, or migration patterns. Disruption of any one of these behaviors, through light pollution, habitat fragmentation, or climate change, can interrupt reproduction. For example, sea turtles return to the same beaches to lay eggs. If those beaches are eroded, developed, or lit up at night, nesting success plummets. Birds that rely on precise seasonal cues to migrate may arrive too early or too late for the insects or plants they depend on. Thanks to shifting climate cycles, dependency on other species can also be a fatal weakness. Some plants are pollinated by only one insect. Some insects feed on only one plant. Some fish rely on coral reefs for breeding. These tight interdependencies make entire chains of life vulnerable to collapse. If one species goes, others may follow, a cascade of co-extinctions. The more connected and specialized an organism is, the more likely it is to fall when its partner does. Human proximity is perhaps the most modern risk factor. Species that live close to human activity, near roads, cities, or agricultural zones, face constant threats: traffic, pollution, pesticides, hunting, noise. Some adapt, others don't. In fact, many species that are now considered critically endangered have been pushed to the edge because they happen to live where humans do, not because they were inherently fragile, but because we moved into their space. Let's look at some examples. The koala is a highly specialized feeder, eating almost exclusively eucalyptus leaves. It has a low reproductive rate, is sensitive to habitat loss, and is vulnerable to bushfires and climate change. Its populations are shrinking quickly in areas where forests are cleared for development. The orangutan, found only in parts of Borneo and Sumatra, lives in forest canopies and has one of the slowest reproductive rates of any mammal. Females give birth once every 6 to 8 years. With habitat destruction from palm oil plantations and illegal hunting, they are disappearing faster than they can recover. By contrast, the raccoon thrives in urban environments. It's an omnivore, a generalist, and an opportunist. It has adapted to human-altered landscapes with remarkable success. While many species decline, raccoons expand their range. The amphibian extinction crisis is another telling case. Amphibians have permeable skin and complex life cycles tied to both water and land. They're sensitive to pollution, disease, temperature shifts, and habitat fragmentation. A fungal pathogen, chytrid fungus, has decimated populations worldwide. It's a global extinction event within a class of animals, and it's happening now. Understanding these patterns helps conservationists focus efforts where they're most needed. If a species is highly specialized, has a limited range, reproduces slowly, and depends on a fragile ecosystem, it's a priority. It needs protection not just from hunting or logging, but from systemic ecological stress. Strategies must be tailored, sometimes protecting a single patch of forest, sometimes controlling an invasive species, sometimes fostering captive breeding. The lesson here is clear. Extinction is not random. It follows rules, patterns, vulnerabilities. It is shaped by biology, behavior, geography, and chance. And by understanding these factors, we gain the power to intervene, to reduce risk, to rebuild populations, to restore balance. But the clock is always ticking. The more we understand vulnerability, the more urgent it becomes to act. Because for many species, vulnerability isn't just a risk, it's a countdown. In the next chapter, we'll shift focus from extinction itself to the ripple effects it causes. What happens to ecosystems when species disappear? How does the loss of one life form reshape entire networks of others? We'll look at the aftermath of extinction, not just what's lost, but what changes in its wake. Extinction is rarely quiet. Though the last individual may pass unnoticed, an unmarked grave in an empty forest or a forgotten pond, the consequences echo far beyond that final moment. The death of a species sets in motion a series of changes, sometimes subtle, sometimes massive. Extinction is never just a disappearance, it's a disruption, a fracture in the delicate architecture of life on Earth. Every species exists within a network of connections. These connections, who eats whom, who pollinates whom, who builds the habitat for whom, make up what ecologists call a food web. It's not a simple chain, but a complex web of interactions. Pull one thread, and others loosen. Snap enough of them, and the entire structure begins to collapse. When a species goes extinct, it removes more than just its own presence. It takes with it its relationships. Consider a plant that depends on a specific pollinator, say a bee species, to reproduce. If the bee disappears, the plant may no longer be pollinated. It will decline, perhaps vanish. But that's not all. Any herbivore that eats that plant, any insect that lays eggs on its leaves, any fungus that lives in its roots, all of these may also suffer, even if they themselves are not directly endangered. This is known as a trophic cascade, when the loss of one species causes a chain reaction through the ecosystem, often across multiple levels of the food web. Perhaps the most famous example involves wolves in Yellowstone National Park. In the early 20th century, wolves were eradicated from the area. With their top predator gone, elk populations grew uncontrolled. Elk overgrazed young trees and shrubs, especially willows and aspens. This altered the structure of riverbanks and forests, affecting birds, beavers, and fish. The entire landscape changed. When wolves were reintroduced in the 1990s, balance slowly returned. The trophic cascade reversed, but only because humans intervened in time. Most extinction cascades, however, are not so easily reversed. The dodo, extinct by the late 1600s, was once a major seed disperser on the island of Mauritius. Its disappearance left certain trees unable to reproduce effectively. In North America, the extinction of the passenger pigeon, once numbering in the billions, left gaps in forest regeneration. These pigeons used to consume and distribute vast quantities of seeds, shaping the composition of hardwood forests. In marine environments, similar dynamics unfold. The overharvesting of sea otters, for instance, led to explosions of sea urchin populations. Urchins feed on kelp. With fewer predators, they consumed entire kelp forests along the Pacific coast, removing critical habitat for fish, invertebrates, and even birds. The loss of one predator led to the decline of an entire marine ecosystem. Some extinctions remove what ecologists call keystone species, organisms that have an outsized influence on their environment. Keystone species hold ecosystems together. Their disappearance leads to disproportionate consequences. Wolves and sea otters are keystone predators. Elephants, which create clearings in forests and dig water holes used by many animals, are keystone engineers. When these species vanish, the ecosystems they shape unravel. Other species play more subtle but equally vital roles. Some are ecosystem service providers. Bees pollinate crops. Bats control insect populations. Vultures dispose of carcasses, preventing the spread of disease. When these species decline or disappear, the impact extends even to human health and economies. In India, for example, the dramatic decline of vultures, due to a veterinary drug toxic to the birds, led to a rise in feral dog populations and associated rabies cases in humans. An ecological gap became a public health crisis. Even the extinction of small or obscure species can have unexpected ripple effects. Soil fungi, ants, amphibians. These aren't headline-grabbing animals, but they regulate processes like decomposition, nutrient cycling, and water filtration. Remove enough of them, and the system becomes less efficient, less resilient, and more vulnerable to stress. There's also a genetic loss that comes with extinction. Every species carries a unique genetic legacy, adaptations to drought, disease resistance, metabolic processes that could one day inspire new medicines or technologies. When a species disappears, that library of information closes forever. It's not just nature that loses, it's human potential. The ripple effects of extinction can also be psychological and cultural. Many communities around the world hold spiritual or cultural connections to local species. Indigenous knowledge systems are intertwined with the plants and animals that surround them. The disappearance of a species can mean the erasure of stories, ceremonies, identities. Even for those without a traditional connection, extinction can provoke grief, what some scientists call ecological mourning. We live in a world where children may grow up knowing more animals from stuffed toys and pictures than from real life. Extinction also affects ecosystem resilience, the ability of a system to absorb shocks and recover. The more species present in an ecosystem, the more backup it has. If one pollinator declines, another might fill its role. If one tree species suffers a disease outbreak, others may carry the forest through. This is the insurance hypothesis of biodiversity. High diversity buffers against uncertainty, but as extinction reduces that diversity, ecosystems become more brittle, more prone to collapse from even small disturbances. One worrying trend is the synergistic effect of multiple extinctions. As more species vanish, the ones left behind often face increased pressure. Their food sources dwindle. Their predators may switch targets. Competition intensifies. Invasive species exploit the new gaps. Disease spreads more easily through simplified systems. Extinction begets more extinction, a domino effect known as extinction debt. In some cases, species may still be alive, but their fate is already sealed due to ecological changes. They are what scientists call the living dead. In human-dominated landscapes, the result of these extinctions is often ecological homogenization. The same few generalist species, rats, pigeons, crows, house sparrows, come to dominate across regions, while unique local species vanish. This creates a world that is biologically poorer, even if superficially still green. We end up with a McDonald's ecosystem. The same few species everywhere, resilient but ecologically shallow. It's worth noting that ecosystems can sometimes adapt to extinctions, especially over long time scales. New species may evolve or migrate in. Ecological roles may be reoccupied. But this process takes thousands, even millions of years. Evolution operates on a timeline far slower than our current rate of destruction. For all practical purposes, especially for humans, extinction is irreversible. Still, there are lessons in these ripples. Understanding how ecosystems respond to loss can help us identify critical species, design better conservation plans, and prioritize restoration efforts. It teaches us not to see species in isolation, but as parts of a living whole. In the end, extinction is not just an endpoint. It is a turning point. Each loss reshapes the future. The death of a species is not just a tragedy of the past, but a question for tomorrow. What will we become without the richness of life that has shaped our world for millions of years? In the next chapter, we will explore the current state of biodiversity on our planet, how we measure it, what we're losing, and why some regions are more at risk than others. The numbers are sobering, but they also point to where action is most needed, and what we still have a chance to save. We live in an age of astonishing scientific discovery. We've mapped the human genome, sent spacecraft to other planets, and unlocked secrets of the universe once thought unknowable. Yet, even as we expand our understanding outward, we are losing something irreplaceable here on Earth: the diversity of life. And we are losing it faster than at any time since the dinosaurs vanished 66 million years ago. This is not a metaphor. The world is now in the midst of what scientists call the sixth mass extinction, a period of accelerated species loss, not caused by natural disaster or asteroid impact, but by the activity of a single species, humans. To grasp the gravity of this crisis, we must understand what biodiversity is, how it's measured, and why it's essential. Biodiversity refers to the variety of life on Earth, from genes to species to entire ecosystems. It's not just about how many species exist, but about the relationships among them, the genetic variation within them, and the ecological systems that sustain them. Measuring biodiversity is complex. Scientists use indicators like species richness, population trends, habitat integrity, and rates of extinction. They gather data from field surveys, satellite imagery, genetic analysis, and increasingly from artificial intelligence and machine learning that can detect patterns at planetary scales. The results are sobering. Current estimates suggest that Earth is home to around 8.7 million species, although some scientists argue the number could be significantly higher, especially when accounting for microorganisms and deep-sea life we've barely begun to explore. Of these millions, only about 1.2 million have been formally described. This means that the majority of life forms remain undocumented, and some may disappear before we even know they existed. Extinction is a natural process. Over Earth's history, species have come and gone. The background rate, the average extinction rate before human influence, is estimated at 1 to 5 species per year. But today extinctions are happening at least 100 to 1,000 times faster than that. According to a 2019 UN report by the Intergovernmental Science Policy Platform on Biodiversity and Ecosystem Services, IPB, 1 million species are at risk of extinction within decades if current trends continue. Let that number settle in: 1 million. This isn't just about iconic animals like tigers, rhinos, or whales. It's about insects, plants, fungi, coral, amphibians, organisms that most people never see, but which form the foundation of ecosystems. A major study in Germany found a 75% decline in flying insect biomass over just 27 years. Insects pollinate 3/4 of our food crops, decompose organic material, and feed countless other species. Their disappearance is a silent alarm. Amphibians are the most threatened vertebrate group. Over 40% of species are at risk. Many are succumbing to a fungal disease called chytridiomycosis, worsened by habitat loss and climate change. Coral reefs too are collapsing under the strain of warming oceans, acidification and pollution. Bleaching events where corals lose their symbiotic algae and starve are becoming more frequent and widespread. In the oceans, overfishing has decimated many populations. Large fish like tuna, cod, and swordfish have declined by up to 90% in some regions. Plastic pollution, dead zones from fertilizer runoff, and deep-sea mining now threaten marine biodiversity across every ocean basin. Meanwhile, forests are being cleared at a rate of around 10 million hectares per year, destroying habitats for countless species. Island species are particularly vulnerable. Over 60% of known extinctions since 1500 have occurred on islands, where species often evolve in isolation and have few defenses against introduced predators like rats, cats, and pigs. The dodo, the moa, and countless flightless rails were wiped out this way. But the biodiversity crisis isn't equally distributed. It is most acute in biodiversity hotspots, regions with extraordinary levels of endemic species and exceptional levels of threat. The Amazon, the Congo Basin, Southeast Asia, Madagascar, and parts of Central America are all under immense pressure. These are places where losing just one patch of forest may mean the global extinction of dozens of species. Why is this happening? The causes are not mysterious. They are well known and well documented. The 5 major drivers of biodiversity loss today are habitat destruction and fragmentation, forests cleared for agriculture, wetlands drained for cities, grasslands plowed under, overexploitation, hunting, fishing, logging, and harvesting at rates faster than ecosystems can recover, pollution from pesticides, industrial chemicals, plastic, sewage and noise, climate change, which shifts temperature and rainfall patterns, alters migration and breeding, and intensifies weather extremes, invasive species, non-native plants and animals that outcompete or prey upon local species, often introduced by humans. These forces are interconnected and often mutually reinforcing. For example, climate change makes habitats less stable, which makes species more vulnerable to disease or invasive competition. Pollution weakens organisms' ability to adapt, while habitat loss isolates populations and reduces genetic diversity. There is a human dimension to this crisis as well. Indigenous peoples, often the stewards of the most biodiverse lands, are displaced or ignored. The commodification of nature, turning forests into lumber, rivers into dams, species into products, has led to both environmental and cultural loss. And while the impacts of biodiversity loss are felt globally, the economic benefits of resource extraction often flow to the few. This crisis is not just ecological, it's economic, social, and moral. Ecosystems provide services worth an estimated $125 trillion per year: clean air, water filtration, crop pollination, climate regulation, and much more. As biodiversity declines, these services weaken, crop yields fall, disease risks rise. Natural disasters become more destructive when wetlands and forests, natural buffers, are removed. There is also the moral dimension. Do we, as the most powerful species on the planet, have the right to erase entire branches of the tree of life? Every extinction is a story that ends, a species that evolved for millions of years, that fit into a system of connections and roles, that can never be replaced. And yet there is still hope. Many species have been pulled back from the brink. The California condor, the Arabian oryx, the black-footed ferret, all were nearly gone, and now survive thanks to sustained conservation efforts. The extinction of the giant panda has been averted, for now, through decades of coordinated international action. Nature can recover if given the chance. To stop this crisis, solutions must be bold, coordinated, and global. Protected areas must be expanded and properly managed. Overconsumption must be addressed. Indigenous rights must be upheld. Laws must be enforced, and conservation must move beyond just charismatic animals to embrace the full web of life, even the unseen, the unlovely, the overlooked. In the final chapter, we'll look at that future, at what we can do, what is being done, and what it will take to truly turn the tide on extinction. Because while the numbers are daunting, the story is not yet over. The next chapter is still being written. The story of extinction, while tragic and often overwhelming, is not only a story of loss, it is also a story of choices, human choices, and the possibility of transformation. The mass extinction unfolding today is not an inevitability. It is the result of systems, behaviors, and values that can be changed. We are not powerless. If we are the primary cause, we can also be the primary solution. Preventing extinction does not rely on a single silver bullet. It requires a symphony of solutions, working together across scales, local, national, and global. It demands science, policy, ethics, and community, all working in harmony. And it begins with understanding that conservation is not about protecting nature from people. It's about reshaping how people live with nature. One of the most effective tools we have is the creation and management of protected areas. National parks, marine reserves, and biodiversity corridors help safeguard the habitat species need to survive. The global target, recently reaffirmed in the Kunming-Montreal Global Biodiversity Framework, is to protect 30% of Earth's land and oceans by 2030. Known as 30 by 30, this target is ambitious, but achievable, if countries follow through with action and ensure protection isn't just on paper. But it's not only about how much land is protected, it's about how it's protected. The best outcomes often come when local communities and indigenous peoples are involved as stewards. Many indigenous territories are rich in biodiversity, and these communities have maintained sustainable relationships with ecosystems for centuries. Empowering these groups with land rights, legal protection, and resources is not only ethical, it's ecologically smart. Another critical strategy is restoration. Damaged ecosystems can recover, forests can regrow, wetlands can be revived, coral reefs can be nurtured back to health. Rewilding initiatives are bringing back lost species and reintroducing keystone animals to revive entire ecosystems. In Europe, bison roam again. In Argentina, giant river otters have returned. The Earth is more resilient than we often give it credit for. We also need to address the drivers of extinction at the source. That includes reducing habitat destruction, especially for agriculture. This means promoting sustainable farming practices, reducing food waste, and shifting toward diets that require less land and fewer inputs. Intensive monocultures and deforestation for soy or beef production, for example, are major causes of biodiversity loss in the Amazon and beyond. A more diversified, regionally adapted food system could feed the world while sparing space for nature. Combating illegal wildlife trade is another essential step. Poaching for ivory, horns, skins, exotic pets, and traditional medicine continues to drive species toward extinction. Strengthening enforcement, improving global cooperation, and reducing demand through education and alternatives can help stop this global industry. Technology, such as DNA forensics and satellite tracking, is giving conservationists new tools to fight back. Pollution control, especially reducing plastic, pesticide, and industrial waste, plays a critical role in protecting both land and marine species. Innovations in biodegradable materials, improved waste management, and tighter regulations can limit the damage we do to ecosystems every day. We must also combat climate change, not just for ourselves, but for every species that shares the planet. Climate action is biodiversity action. Slowing global warming will help stabilize ecosystems, reduce habitat shifts, and give species time to adapt. This means reducing emissions rapidly, protecting carbon sinks like forests and peatlands, and investing in renewable energy and green infrastructure. Then there's science and monitoring, the foundation of informed action. We can't protect what we don't understand. Continued investment in field research, species discovery, and population monitoring is essential. This includes using citizen science platforms, AI-powered tracking, and satellite imaging to detect trends, identify at-risk areas, and measure conservation success. One of the more powerful yet underutilized tools is legislation. Laws can compel action and ensure accountability. The U.S. Endangered Species Act, for example, has helped prevent the extinction of dozens of species, from the bald eagle to the gray wolf. Similar laws around the world, when properly enforced, provide a safety net for the most vulnerable. But policy alone isn't enough. Preventing extinction also means shifting cultural values. In many societies, biodiversity is seen as optional, as a luxury or a decoration. We need a new narrative, one that treats nature not as a backdrop, but as a co-creator of life. This involves education, media, art, and storytelling. It involves raising children to recognize the calls of birds, the names of plants, and the idea that other species are not just objects, but fellow travelers on this earth. Technology can also play a role. Gene banks and conservation breeding programs are preserving genetic material of endangered species. In some cases, de-extinction efforts are exploring whether certain extinct species could be revived. These are controversial, ethically complex, and not a replacement for preventing extinction in the first place. But they point to the potential of biotech in conservation science. Importantly, urban environments can be part of the solution. Cities can become sanctuaries, with green roofs, native plant corridors, and biodiversity-friendly planning. Urban conservation may not save tigers or elephants, but it can support pollinators, birds, bats, and amphibians. It also connects people to nature, which is essential for building the will to protect it. Finally, there's the matter of hope. Hope is not passive, it is not pretending things are fine. Hope is the belief that with effort, things can get better, and the motivation to act accordingly. It means recognizing that we are at a crossroads, and choosing the path that leads toward a livable planet for all. Yes, extinction is real, and it is happening, but it is not inevitable for every species at risk. With enough knowledge, resources, and will, many can still be saved. The giant panda, the mountain gorilla, the California condor, all once symbols of hopeless decline, are now symbols of what's possible when people care, coordinate, and commit. The biodiversity crisis is in the end a mirror. It reflects the systems we've built, the priorities we hold, and the future we choose. It challenges us not just to protect animals and plants, but to protect the planet's capacity for wonder, balance, and resilience. This is not just about extinction, it is about survival, of ecosystems, of humanity, of hope itself. We still have time, but not forever.